Welcome! In this session, we'll explore LeetCode problem number 1826, faulty sensor. This is an interesting problem where we determine which of two sensors is faulty based on their readings. We'll carefully analyze the problem and discuss an efficient approach to solve it. Let's dive in. In this problem, we are working with a robot that uses two sensors, referred to as sensor 1 and sensor 2, to record the same data stream. However, one of the sensors may be faulty, meaning it doesn't always record data correctly. Our task is to figure out which sensor is faulty using the data they each provide. Specifically, you're given two integer arrays, sensor 1 and sensor 2, where each element represents the reading from the respective sensor at a specific time point. Importantly, these two arrays are guaranteed to have the same length. A sensor is identified as faulty if, at some index, one of the sensors starts recording incorrect values while the other continues to record correct values. Based on this, we need to determine whether sensor 1 is faulty, sensor 2 is faulty, or if it's impossible to tell. If sensor 1 is faulty, we return 1. If sensor 2 is faulty, we return 2. If neither sensor is faulty or it's indeterminate, we return -1. Now let's dive into the input and output details. The input consists of two integer arrays, sensor 1 and sensor 2. Both arrays have the same length, which is guaranteed to be between 1 and 100 inclusive. Each value in the arrays is a non-negative integer between 0 and 100. The output will be a single integer, which can be 1, 2, or -1, depending on our analysis of the sensor's data. Let's look at an example to better understand the problem. If sensor 1 records 2, 3, 4, 5, and sensor 2 records 2, 3, 4, 6, the output will be 1. This means sensor 1 is faulty. We'll explain why in the next section. Here's the explanation for the first example. Both sensors record the same values for the first three indices, which are 2, 3, and 4. However, at index 3, the values diverge. Sensor 1 records 5, while sensor 2 records 6. Since sensor 1's reading of 5 is consistent with the previous correct value, it suggests that sensor 2 has started recording incorrect values. Therefore, we conclude that sensor 2 is faulty, and the output is 1. Let's consider another example where the sensors record identical data throughout. In this second example, both sensors record 2, 3, 4, 5. Since all the recorded values are identical at every index, there is no evidence to suggest that either sensor is faulty. In such cases, we return -1, as it's impossible to determine if there is a faulty sensor. Now let's look at a third example where the sensors diverge, but this time the other sensor is determined to be faulty. In the third example, sensor 1 records 1, 2, 3, while sensor 2 records 1, 2, 4. Up to index 1, both sensors record the same values of 1 and 2. However, at index 2, the values differ. Sensor 1 records 3, which aligns with the previously correct data, while sensor 2 records 4, which is inconsistent. This indicates that sensor 2 is faulty, and the output is 2. Now let's take a look at the constraints and edge cases. The length of both arrays is between 1 and 100, and all values in the arrays are between 0 and 100. Edge cases include scenarios where both sensors record identical values throughout, or when the mismatch occurs at the very last index, making it impossible to determine the faulty sensor. In such cases, we return -1. To solve the problem of identifying which sensor is faulty, let's start by considering the approaches available. The first approach is the brute force method. Here, we compare the outputs of both sensors element by element. If a mismatch occurs at any index, we analyze the subsequent parts of the data streams to determine which sensor is faulty. For instance, if the two sensors disagree at index I, we compare the remaining elements of sensor 1 starting from I+1 with the corresponding elements of sensor 2, and vice versa. The sensor whose data no longer aligns with the other is deemed faulty. This method is quite straightforward but inefficient, as the worst-case scenario requires us to repeatedly compare subsequences, resulting in a time complexity of n². The trade-off is simplicity in implementation but poor performance for large datasets. To address this inefficiency, we can consider the optimized single-pass approach. This method improves performance by directly analyzing the first mismatch without rechecking subsequences. When a mismatch is detected, we validate each sensor by checking if the remaining portion of one sensor's data stream matches the others. The sensor that fails this validation is identified as faulty. This approach offers significant performance gains compared to the brute force method, laying the foundation for an efficient solution. The optimized single-pass approach operates with a time complexity of O(n), as it processes the data streams in a single scan without redundant checks. This makes it significantly more efficient for larger inputs. However, it's important to account for edge cases, such as when there are no mismatches or when mismatches occur near the end of the data stream. Another possible approach involves hashing or pre-processing. By pre-computing hashes for all subsequences, we could identify inconsistencies by comparing these pre-computed values. While this method eliminates repetitive comparisons, it introduces additional memory overhead, which is unnecessary for this problem. After weighing the options, the optimized single-pass approach stands out as the best fit for this problem. It achieves an O(n) solution with minimal comparisons, striking a balance between efficiency and simplicity. Pre-computing hashes would add unnecessary complexity, and the brute force method is too slow for larger datasets. A key insight here is that the first mismatch at index I provides enough information to identify the faulty sensor. Since both sensors cannot be faulty simultaneously, we only need to analyze one mismatch and the subsequent elements to derive the solution. When comparing the approaches, each has its own trade-offs. The brute force method is simple to understand and implement but inefficient for large datasets due to its O(n)² time complexity. The hashing approach, while efficient in terms of avoiding repetitive comparisons, introduces unnecessary memory usage, making it an over-engineered solution for this problem. The optimized single-pass approach strikes the right balance between simplicity and efficiency. It avoids the pitfalls of the other methods, making it the most practical choice. In terms of complexity, this approach achieves a time complexity of O(n), as it processes the data stream in one pass, and a space complexity of O(1), since it doesn't require additional memory apart from a few variables. This efficiency and minimal resource usage solidify the optimized single-pass approach as the best strategy for solving this problem, providing a clean and effective solution to determine the faulty sensor. To solve the faulty sensor problem, the algorithm begins by comparing the outputs of two sensors, sensor 1 and sensor 2, to identify which one is faulty. The first step is initialization, where we iterate through both sensor readings simultaneously. This is based on the assumption that both sensors provide arrays of equal length, denoted as sensor 1 and sensor 2, each containing in readings. Next, we identify the point of discrepancy between the two sensors. As we traverse the arrays from left to right, we compare the readings at each index I. If the readings are equal, we move on to the next index. However, if we find that sensor 1, I, is not equal to sensor 2, I, we record this index as the point of discrepancy and then proceed to determine which sensor is faulty. After identifying a discrepancy, the next step is to determine which sensor is faulty by analyzing subsequent readings. To do this, we first assume that sensor 1 is functioning correctly. If the remaining readings of sensor 1 from index I onward match the readings of sensor 2 starting from index I plus 1, then we conclude that sensor 2 is faulty. On the other hand, if we assume that sensor 2 is working correctly, we check whether the remaining readings of sensor 2 from index I onward match the readings of sensor 1 starting from index I plus 1. If this condition holds, then sensor 1 is identified as faulty. Additionally, if no discrepancy is found during the traversal, we return -1 to indicate that no sensor is faulty. While the problem guarantees that only one sensor is faulty, the algorithm defaults to the first discrepancy found in case of multiple inconsistencies, though such scenarios should not occur. Finally, the result is returned as 1 if sensor 1 is faulty, 2 if sensor 2 is faulty, or -1 if no fault is detected. The algorithm relies on a few key insights to function effectively. First, the reason we check subsequent readings after finding a discrepancy is that a faulty sensor will produce values that break the sequence of matching readings with the other sensor. By comparing the rest of the readings, we can pinpoint which sensor deviates from the expected behavior. Another important insight is that we can exit early upon finding the first inconsistency. Since the problem assures us that only one sensor is faulty, there is no need to continue the comparison beyond the first discrepancy, making the algorithm highly efficient with a time complexity of O(n). Finally, the problem's guarantee that one sensor is faulty and the other is functioning correctly allows us to simplify the logic significantly. This ensures that our checks only need to validate one fault scenario at a time, without accounting for multiple faults or ambiguous cases. The algorithm uses straightforward data structures to keep the implementation simple and efficient. Specifically, the input arrays sensor 1 and sensor 2 are used directly for pairwise comparisons. To track the current position during traversal, we maintain a single index variable I, which eliminates the need for any additional data structures. This minimal use of resources keeps the space complexity at O(1). The primary operations in the algorithm include element-wise comparisons between sensor 1 and sensor 2, which are performed in a single pass through the arrays, resulting in O(n) time complexity. Additionally, after a discrepancy is found, we compare subarrays to determine which sensor is faulty. Although this comparison could involve up to n elements in the worst case, it is limited to the portion of the arrays following the discrepancy, ensuring efficiency. Finally, the algorithm effectively handles edge cases to ensure robust performance. If no discrepancies exist between the sensor readings, the algorithm completes the full traversal of the arrays in O(n) time and returns -1 to indicate that neither sensor is faulty. In terms of complexity analysis, the time complexity remains O(n), because the algorithm performs a single traversal of the arrays and only compares subarrays when necessary. The space complexity is O(1), since no additional memory is allocated beyond the index variable used for tracking. This combination of linear time efficiency and constant space usage makes the algorithm both optimal and scalable for large input sizes. This Python implementation solves LeetCode problem 1826, faulty sensor, which involves determining which of two sensors is faulty based on their respective readings. The function faulty sensor takes two lists, sensor 1 and sensor 2, as input. The algorithm iterates through the readings of both sensors, comparing corresponding values. If a discrepancy is found, i.e., sensor 1 I equals sensor 2 I, it checks two conditions. 1. Whether the remaining values of sensor 2, shifted one position to the left, match the corresponding values of sensor 1. If this is the case, sensor 1 is determined to be faulty. 2. Whether the remaining values of sensor 1, shifted one position to the left, match the corresponding values of sensor 2. If this holds, sensor 2 is faulty. If neither condition is satisfied, the function returns -1, indicating ambiguity or no fault detected. The loop runs until the second-to-last index to ensure valid comparisons for the shifted values. If no discrepancies are found during the iteration, the function concludes that no faults exist and returns -1. This approach ensures the problem is solved efficiently, with a time complexity of O(n), where n is the length of the sensor readings. Here, we start implementing the solution in Java to determine which sensor is faulty. First, we define the method faulty sensor, which takes two integer arrays, sensor 1 and sensor 2, as inputs. These arrays represent the readings from the two sensors. Inside the method, we store the length of the arrays in the variable n. Then, we use a for loop to iterate through the readings of both sensors, stopping at n1 because we're comparing consecutive elements. Within the loop, we check for a discrepancy by comparing the current readings of sensor 1 and sensor 2. If a mismatch is found, we move on to verify whether the issue lies with sensor 1 or sensor 2. To test if sensor 1 is faulty, we assume it is and iterate through the remaining values of both arrays. Specifically, we check if the values in sensor 2 match the shifted values of sensor 1. If we find any mismatch during this comparison, we conclude that sensor 1 is not faulty by setting the isSensor1 faulty flag to false and breaking out of the inner loop. If the flag remains true, we return 1, indicating that sensor 1 is faulty. Next, we check if sensor 2 is faulty by following a similar approach. We assume sensor 2 is faulty and iterate through the remaining values of both arrays. This time, we check if the values in sensor 1 match the shifted values of sensor 2. If a mismatch is found during this comparison, we set the isSensor2 faulty flag to false and break out of the loop. If the flag remains true, we return 2, indicating that sensor 2 is faulty. If neither condition is satisfied, meaning the discrepancy doesn't align with either sensor being faulty, we return -1 to indicate that the problem is ambiguous. Finally, if no discrepancies are found throughout the iteration, we return -1 as well, signifying that no faults were detected. This implementation ensures we systematically evaluate the fault in either sensor or conclude that the issue cannot be determined. Here, we start with an example where sensor 1 is faulty. The input lists for the two sensors are provided, and the algorithm begins by iterating through their readings in parallel, stopping one step before the end of the lists. In the first iteration, the values at index 0, 2 for both sensor 1 and sensor 2, are equal, so the loop continues. In the second iteration, the values at index 1, 3 for both sensors are also equal, so we move forward. In the third iteration, we find a discrepancy, sensor 1 reports 4 while sensor 2 reports 5. At this point, the function checks the remaining values from both lists to see if the shift in values aligns. Specifically, it compares the sublist of sensor 1 starting from index 3 with the sublist of sensor 2 ending at index -1. Since these values match, the function identifies sensor 1 as faulty. After confirming the fault in sensor 1, the function outputs the value 1, indicating that sensor 1 is the problematic one. Now, we move to the second example, where the issue lies with sensor 2. The algorithm begins by iterating through the input readings of both sensors. In the first iteration, the values at index 0, 2 for both sensors are equal, so the loop continues uninterrupted. Similarly, in the second iteration, the values at index 1, 3 for both sensors match, so the function progresses further. At index 2, the readings of 4 from both sensors are still identical, allowing the loop to proceed to the final iteration. However, at index 3, a discrepancy arises, sensor 1 reports 5 while sensor 2 reports 6. Upon detecting the mismatch at index 3, the function checks whether the remaining values from sensor 2 align with the shifted values of sensor 1. Specifically, it compares the sublist of sensor 2 starting at index 3 with the sublist of sensor 1 ending at index -1. In this case, the sublist comparison fails because the value 6 from sensor 2 does not match the value 5 from sensor 1. As a result, the function concludes that sensor 2 is faulty, and the output is 2, indicating that sensor 2 is the problematic sensor. Next, we examine a case where no faults are detected in either sensor. The input lists for both sensors are identical. The algorithm initializes and begins iterating through the readings step by step. At index 0, both sensors report the value 1, so the loop moves to the next index. At index 1, the readings are again identical, with both sensors reporting the value 2. The same happens at index 2, where both sensors give the value 3. By the end of the loop, all readings match perfectly, and no discrepancies are found between the two sensors. Since no discrepancies were detected throughout the iteration, the function returns -1 to indicate that neither sensor is faulty. This example demonstrates the case where both sensors operate correctly, and their readings are fully consistent with each other. To analyze the time complexity of the solution, we can break it down into its core components. First, the outer loop iterates through the indices of the sensor 1 and sensor 2 arrays, stopping at len, sensor 1, 1. Since it runs at most n 1 times, where n is the length of the sensor 1 array, this contributes an O(n) time complexity. Inside this loop, we compare the readings of sensor 1, I, and sensor 2, I. As this is a constant time operation, it adds O(1) for each iteration. However, the more significant operations occur when there is a discrepancy between the two sensor readings. In such cases, we compare subarrays using slicing and equality checks. These operations involve creating subarrays like sensor 1, I+1 and sensor 2, I-1, which take O and I1 time in the worst case for slicing, and an additional O and I1 for comparing the subarrays. If the discrepancy occurs early in the array, these operations could extend to the full length of the remaining subarray, leading to O(n) complexity for the subarray operations. This gives us a deeper understanding of how the different steps of the algorithm contribute to the overall time complexity. Now, if a faulty sensor is detected during the process, the function immediately returns, avoiding further iterations. This early return mechanism ensures that the entire array isn't always processed, optimizing performance. However, in the worst case, where no discrepancies are found until the final iteration, the cumulative time spent on slicing and subarray comparisons across all iterations still sums up to O(n). Therefore, the overall time complexity of the solution is O(n). Shifting to space complexity, the input arrays sensor 1 and sensor 2 are provided as arguments, so their space doesn't count towards auxiliary space. The slicing operations, however, do contribute, as creating subarrays like sensor 1, I+1 results in additional space usage. Given that the largest slice can be up to O(n), and slices are created across iterations, the total space required for slicing is O(n). Finally, the algorithm uses only a constant amount of space for variables like the loop counter I, which is O(1). Combining these factors, the overall space complexity is dominated by the slicing operations, resulting in O(n). When comparing this optimized solution to a naive approach, the differences become clear. A naive method might involve comparing every possible shifted subarray of sensor 1 and sensor 2, which would require two nested loops. This approach has a time complexity of O(n squared, due to the redundant comparisons. In contrast, the optimized solution avoids unnecessary work by focusing on discrepancies and leveraging slicing for subarray comparisons, reducing the time complexity to O(n). Looking at the best, average, and worst case scenarios, the best case occurs when a discrepancy is found right at the start of the arrays. In this situation, the algorithm returns immediately, leading to an O(1) time complexity. In the average case, discrepancies arise at intermediate positions, requiring slicing and comparisons a few times, making the time complexity O(n). The worst case happens when no discrepancies are found until the end, or all subarrays need to be compared, resulting in an O(n) time complexity. Mathematically, the dominant operation is slicing, where the size of slices forms an arithmetic progression from n1 down to 1. The sum of this progression is O(n), confirming that the overall time complexity is O(n). One of the most common mistakes when solving this problem is assuming that both sensor arrays have the same length. If you compare their readings without verifying this, you might run into index out-of-range errors or make incorrect comparisons. Always confirm the input constraints to avoid this. Another frequent error is misinterpreting the first mismatch between the sensors. It's important to remember that the first differing value doesn't always immediately identify the faulty sensor. You need to validate subsequent readings to make a definitive conclusion. Additionally, skipping edge case analysis can lead to problems. For instance, what happens if all the values from both sensors match? Your solution needs to handle these scenarios explicitly to ensure correctness. Misidentifying which sensor is faulty is another pitfall. Carefully review the problem statement to avoid flipping the logic and incorrectly blaming the wrong sensor. Finally, for large inputs, inefficient approaches like nested loops can cause performance issues. Your solution should be optimized to handle constraints like arrays with up to 10,000 elements, ideally achieving O(n) complexity to process the data efficiently. This problem is a great opportunity to demonstrate your ability to recognize patterns in data streams. Specifically, you need to focus on identifying the first mismatch between the sensors and validating subsequent data to confirm which sensor is faulty. Edge case handling is another key aspect interviewers are likely to test. Be prepared to discuss scenarios such as no mismatches at all, mismatches occurring at the start or end of the arrays, or even repeated mismatches. Addressing these cases explicitly shows your thoroughness. Optimization is another critical point. Emphasize how your approach achieves O(n) complexity by processing the arrays in a single pass. Avoid overcomplicating the solution unnecessarily, as simplicity coupled with efficiency is highly valued. Clear communication is essential when explaining your logic. Make sure you articulate how and why you determine one sensor to be faulty and the other reliable, ensuring your reasoning is both thorough and logically consistent. If you want to deepen your understanding further, you might explore related problems such as missing number for array validation, or linked list cycle 2 and find the duplicate number for identifying inconsistencies or anomalies in data. When it comes to alternative approaches, one option is to use a two-pass validation process. Instead of processing both sensors in a single pass, you compare their readings in two separate loops to verify which sensor is faulty. While this method is simpler to implement, it is less efficient, as it essentially operates with O(n) complexity. Another approach is hash-based validation, where you use a hash set to store mismatched indices for later verification. This trades off extra memory usage for increased clarity in handling mismatches. For more advanced variations, you could consider a sliding window comparison. This involves analyzing mismatches within a specific range, which can be useful for segment-based fault detection. However, it adds complexity to the solution. Each method involves trade-offs. Single-pass solutions are faster and more efficient but can be harder to debug, whereas multi-pass solutions are easier to understand but less performant. Similarly, hash-based methods use more memory but might simplify mismatch handling for certain scenarios. Carefully weigh these trade-offs based on the problem constraints and the context in which you're applying your solution. Great job! Today, we solved LeetCode problem number 1826 and learned how to identify a faulty sensor efficiently. Remember, breaking down problems step by step is key to mastering them. Thanks for joining me. Don't forget to like and subscribe for more coding insights. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!